Most of our electronic devices seem to break all of a sudden. A phone works normally in the morning, then its battery starts draining rapidly in the afternoon. A laptop runs quietly for years, and one day its fan begins to roar. In such situations, there is usually no single major failure. What we observe instead is the accumulation of small shocks. In engineering, this is called the shock model. A shock does not have to be dramatic. Voltage fluctuations, temperature changes, loose contacts, dust, or repeatedly turning a device on and off all count as shocks. Each shock leaves small damage that the system initially tolerates. Over time, the system weakens until a once harmless shock becomes enough to cause a failure. At this point, two questions become central. First, what's the probability the system is still working? We call this reliability or survival probability. If shocks are frequent or intense, this probability drops more rapidly. Second, what is the system's average time to fail? This is called the mean time to failure. For businesses, maintenance planning and cost calculations rely on this value. In everyday terms, the question is simple. How long will this device last me? Most systems deteriorate gradually rather than failing at a single moment. A phone battery loses capacity and screen brightness fluctuates. A refrigerator runs longer, consumes more energy, and eventually the compressor strains. When air conditioner filters clog, even a minor shock can lead to overheating. The system moves from full performance to a fatigued state, and eventually to a critical state. Notably, the same device can have very different lifespans in different houses. Where voltage is stable, conditions are clean, and usage is moderate, the device lasts longer. Where electricity is unstable, humidity is high, and usage is heavy, the reliability curve shifts accordingly. This is why a 2-year warranty does not always mean the same thing in practice. Small precautions can therefore make a significant difference. Surge protectors, cool environments, clean filters, and avoiding excessive heat all reduce the impact of shocks. The same logic applies to buildings and humans. In buildings, small earthquakes, temperature differences, and humidity fatigue structural elements over time. In the human body, sleep deprivation, stress, poor nutrition, and repeated minor injuries function as shocks. At first we cope. Later, the same load causes greater damage. In conclusion, shock models view failure not as a random event, but as a cumulative process. They track survival probability, calculate average lifespan, and manage maintenance based on accumulated risk rather than fixed schedules.